Hello students, welcome back. We just completed section 1 in which we studied quadratic residue. We defined it and we studied it in terms of quadratic congruence. We went through a couple of example problems as well, and there, checking whether a given candidate, given integer is congruent to a quadratic residue or not was a big problem. Here, we have only modulo 13, so we tested everything from 0 to 12. But what if we have a prime number with 13 digits? Good luck trying everything. We need a little bit better tool. What better tool do we want? This one right here, Euler's criterion. Let P be an odd prime and P does not divide A. In other words, A is non-zero mod P. Then A is a quadratic residue of P if and only if A to the P minus 1 over 2 power is congruent to 1 mod P. In fact, if that's congruent to 1, then quadratic residue. If that's congruent to negative 1, then quadratic non-residue. And in the third case, this is congruent to 0 because A is going to be 0. So that's how we can classify everything. This way, we don't have to test everything. We can test it for that particular integer and that's it. Of course, in order to prove it, we need some preparations, and that's what this 2.1 is all about. Let's have some review from lesson 12. If A and M are relatively prime and the order of A mod M is phi of M, the value of Euler torsion function, then A is called a primitive root of unity modulo M, or simply a primitive root of M. Remember that? And then if A is a primitive root of M, then we have this interesting property. Every integer relative prime to M is congruent to some A to the R power, where R is from 0 to phi of M minus 1. And we have congruence modulo phi of M in the powers for R, and that is equivalent to the congruence of A to the R power mod M. Remember that too? The distinctness property of the modular order. And then what else do we have? Oh yes, there are exactly phi of P minus 1 primitive roots of any prime. Okay, those are the kind of important things from lesson 12 that we are going to be using here. Keep those in your mind, and let us go ahead to 2.2, Euler's criterion. Let P be an odd prime and P does not divide A. In other words, A is non-zero mod P, or still equivalently, P and A are relatively prime. Then A is a quadratic residue of P if and only if A to the P minus 1 over 2 power is congruent to 1 modulo P. This one here, that's Euler's criterion. Yeah, like this. Okay, how do you prove that? Let's consider the forward direction. So if there is a square root, if there is a solution to this congruence, x squared is congruent to A mod P, then getting this is not too bad. It's pretty easy. Let alpha be the solution. So alpha squared is A. Then A to the P minus 1 over 2 is alpha squared to the P minus 1 over 2, isn't it? Yeah. So this second power and this denominator cancel out. We end up with alpha to the p minus 1 power. And that's always 1 by Fermat theorem. It's that simple. So one direction is really simple. It follows immediately from Fermat's theorem. Instead of alpha, I use another character. I use x1. That's fine. Okay, we have one direction. How about the other direction? Now that's going to be a work. We have to follow multiple steps, and let's try to complete it in a single video. Alright, let R be a primitive root of P, which exists because P is prime. Remember? Primitive root exists modulo P, and how many are there? Phi of P minus 1 of them, or phi of P of them. So R exists. Let R be a primitive root of P. So what do you mean by that? R to the nth power is congruent to 1 mod P, a minimum of such n, that's the order of R modulo P, and that has to be phi of P, which is P minus 1. So R to the P minus 1 power is consequently 1 modulo P, and then anything less than that P minus 1 power, they're all different, not 1. Then, for some integer k, a is congruent to r to the k power modulo p. What property did I just use? This one right here. Different character, yeah, but that's what I use. Any integer is congruent to a to a certain power like this if the base is a, but this time base is r, so we have r to the k power. So this 2 came from lesson 12. Now if k is even, then we are through. So we can have r is k over 2 power. So if this thing squared and r of k of 2 power square again, then k power, and we are going to come back to a. So we have a solution. Therefore, a is a quadratic residue. Now, what if odd? What if k is odd? Then we claim we get a contradiction, so that's impossible. A is 2i plus 1 power. It's an odd power, so let's write like this. And then a to the p minus 1 over 2 power, let's put it into just r to the 2i plus 1 power in place of a. And we need a lot of powers. So let's increase the font so that you can look at those powers in a little bit more detail. 2i plus 1 power replaces a, and then p minus 1 over 2 power. Okay. And then we can apply the distribution, this time 2i, and then this 2 in denominator cancel out, and we have, oh, excuse me. Okay, alright, sorry about that. I times p minus 1 power. We get that because we have to multiply this 2i times this power. And then this power times 1, which is the ladder here. Okay. Now, what is this? This is 1 by Fermat theorem. R to the p minus 1 power is 1, and that's to the I power. That's 1 by Fermat's theorem. So we just have r to the p minus 1 over 2 power. And we claim that cannot be 1. Why not? Because r is a primitive root of p. So r to the p minus 1 power is 1, but anything less than p minus 1 power, we cannot have 1. Remember, the order of A modulo P, or the modulo P, order of R modulo P, excuse me, basis R this time, the order of R modulo P is given by the minimum. The minimum is P minus 1, and this is less than the minimum, so it cannot be 1. So R is primitive, so this is not 1. So what do I get? A to this power is not 1. We are doing the opposite direction here, and it contradicts with our assumption. Well, this is a kind of defect of having big font. I cannot see everything in this single viewing window. See this? It contradicts with this assumption. So we cannot have an odd prime. It has to be even, in which case, yeah, we are true. A is a quadratic residue. Now, as for the second part, okay, let's go. Either a to the p minus 1 over 2 power is 1 mod p or negative 1 mod p. Okay, so either 1 or negative 1. Moreover, if congruent to 1, then A is a quadratic residue, so such an X exists. If congruent to negative 1, then by the first statement we prove this is quadratic non-residue. Such X does not exist. The second claim comes immediately from the first one that we proved, so that's not very important. We're going to prove that this or that a to the p minus 1 over 2 power is 1 or negative 1. Proving that is going to be sufficient. Okay, how do you prove that? Due to Fermat's theorem, multiply those two. P minus 1 over 2 power minus 1, p minus 1 over 2 power plus 1, just multiply those two. And then we have a to the p minus 1 power minus 1, and that's always 0 by Fermat's theorem. So what do you have? Blue times green is 0 modulo p, and p is prime. Therefore, either blue is 0 or green is 0. By Euclid lemma, either one of them is 0. There is no 0 divisor. So blue is 0, in which case a to the p minus 1 over 2 power is 1, or green is 0, in which case a to the p minus 1 over 2 power is negative 1. So we got the main statement, either 1 or negative 1. And then if we apply the previous result, then congruent to 1, then quadratic residue. Congruent to negative 1, then not a quadratic residue, but we already assume p is not dividing a, so a is non-zero. So actually this is quadratic non-residue. A being equal to 0 is already out of consideration. So that completes the proof of Euler's criterion.